Hello students. In this lecture, we'll continue with your unit number 2, that is heat transfer through the extended surfaces. And this is going to be the lecture number 4, where we are going to solve some of the problems which are from the fins, extended surfaces. So, we'll do some introduction initially, then we'll solve first numerical on the fin with insulated tip, what we call adiabatic fin in short. Then we'll solve one numerical on the infinite fin, and we'll solve one more problem for the calculation of fin performance. And with some closing remark, we'll end. This fins or extended surfaces, if you recall the things, we have started with the definition of the fin or extended surfaces. Then we have analyzed the fins along with a generalized conduction equation for the fins. We have reduced that equation for a fin with constant cross-section area, that is what you call pin fins. Then we have found out the solution of that generalized conduction equation, rather reduced generalized conduction equation for two conditions. One is fin with adiabatic tip and the other one is fin with insulated tip. Fin with infinite length. So adiabatic fin means the fin in which the tip heat transfer rates reduce to zero. So we can assume that there is no heat transfer from the fin tip, and that's why the fin tip can be treated as a fin with insulated surface, and the temperature gradient at that location can be assumed equal to zero. Then after learning about or finding out the temperature distribution for both the types of fins, we have calculated, we have derived equations for finding out the rate of heat transfer from the fins. Then in the last lecture, we had a discussion about fin performance parameters like fin effectiveness and fin efficiency, their relevance. We also discuss about what is the meaning of proper length of the fin and what is the meaning of infinite length of the fin. So all this background, all these equations which you have derived in the last few lectures, we are going to apply them, we are going to use them for finding out the different parameters as per the requirement of this particular situation. So let us one by one, we'll have three numericals, and once again I would like to remind you, in the heat generation problem also, or one dimensional steady state conduction without heat generation also, while discussing about the numericals, I told you that you please note down the numerical on your notebook, try to solve the numerical at your own. During that period, pause the video, try to solve the numerical, then continue with the video, find out whether your solution is correct or wrong. If it is wrong, where it has gone wrong, and then you can continue for the next problem. One more important aspect I would like to tell you about the fins problem, that most of the data is available in the problem itself, and we have got already the equations for different types of fins. So it is just the identification of which boundary condition is applicable to the given problem. Based on that, we can select a proper set of equations. We can just put the values in those equations, of course taking care of the conversion of the units, and then simply we can calculate the required parameters. So almost most of the problems are just putting the values and getting the answer directly. Of course, a lot of understanding is required for finding out which particular set of equation is required, and then only the calculations are going to be correct calculations. So with this background information, I would like to start with the first numerical. Myself, Nitin Elvirud, working as an associate professor in Sandeep Institute of Engineering and Management. So let us start with our first example, a brass rod. Note the material, it is brass. Brass is having a thermal conductivity in the order of 100 to 110 watt per meter Kelvin. So brass is also a suitable material for the fins because of its higher thermal conductivity. Is in the form of 100 millimeter long and 5 millimeter diameter. Once again, I'd like to interrupt. See, the length is 100 millimeter, but the diameter is only 5 millimeter. In the last lecture, while discussing about the fin effectiveness, I told you that the effectiveness of the fin is more if the ratio for the area of cross section to the perimeter to the area of cross section is higher. So that's why we are using the fins with smaller dimensions, smaller diameter, smaller thicknesses. So you can please note this. Extend horizontally from a casting which is at 200 degrees Celsius. So base temperature for us is 200 degrees Celsius. The air temperature is 20 degrees Celsius. Fluid temperature is 20 degrees Celsius and the heat transfer coefficient is 30 watt per meter square Kelvin. What is the heat transfer from the rod? Evaluate temperature of the rod 50 millimeter from the base and at the free tip. Now the length is already known 100 millimeter and it's not too long. So we can safely assume that the fin is with insulated tip and we can solve this problem. So identification of our understanding gives us that the length is not so large. So we can use the fin with insulated tip assumption in this problem. So what is given? We got a brass rod, length L is equal to 0.1 meter, H is 30, D is 0.005 meter, conductivity of brass is 380. It's actually very large value given, but let us accept it. And temperature of surface is 200 degrees Celsius and the fluid temperature is 20 degrees Celsius. So if you draw the fin, there's going to be fin base at temperature say Ts, which is 200, T infinity is 20, heat transfer coefficient is 30. So what is required? We need to find out what is the rate of heat transfer, what is the temperature at x is equal to 50 millimeter, means at the center of the fin, and what is the temperature of x is equal to L. So we need to use two equations basically, the temperature distribution equation for finding out these two temperatures and the rate of heat transfer equation for finding out the rate of heat transfer from the fins. So let us assume certain things, that steady state, negligible radiation, uniform value of H, and in the infinity one dimensional conduction in x direction only, constant properties, unknown properties, and finally the fin with insulated tip. So with this assumption, let us try to solve this. First, let us find out the parameters like perimeter, geometrical parameter. So it is pi into d, found to be 0.0157. Area of cross section is pi by 40 square, circular. So it is 0.000196 meter square. So with this data, also we need the value of theta b, that is the value of temperature difference at the fin base, that is Ts minus T infinity 200 minus 20, and that is 180 degree Celsius. So we got perimeter, cross sectional area, and the value of base temperature or base value of theta b. Then we can calculate m as under root hp upon kc, just putting the values hp into kac. Already we have got p and ac, so we can directly put those values, and h is already known, k is given 380, and h was found to be 7.947. Just note the unit of m, it is m raised to power minus 1, means 1 upon meter. So if it is multiplied, this m is multiplied by L, ml, then m is 1 upon meter, L is meter. So it is going to get cancelled and ml will become a dimensionless term. Or we can call that ml as a dimensionless length. And that's why you may recall that while discussing about the infinite length of the fin, proper length of the fin, we have taken into consideration this parameter ml because it is a dimensionless parameter. It is not dependent on any other aspects of the things. It is a dimensionless thing. So whether the fin is triangular cross section, rectangular cross section, whatever, ml is ml. It is not dependent on the geometrical conditions. Using the equation for the heat transfer from the fin with insulated tube, what is the equation? The equation is under root hp into kac into theta b into tan hyperbolic ml. So already we have got m, we know L, we know h, we know p, we know k, we know ac, we know theta b. So everything is there, just putting the values into this equation. Yes. Now in the examination, I'd like to tell you that it is expected that you need to write down in this same fashion. See, equations are to be written, no doubt, with some commentary. Then writing down the values is also equally important. This is very important because here there are chances of making a mistake, because if you are not putting the values in proper units, then you may lead into a wrong answer. So while writing it in the examination also, it is advisable to write down the values so that you will get clear cut idea what we are writing and what we are calculating. Although your calculators may have the capacity to calculate all these simple equations directly, but it's my advice that you should not rely on those things, and you should write down the values and then you can calculate. And it was found to be 6.87 watt, very small although, but the rod is also small and single rod, so it is according to that dimensions. Now we are interested in finding out the temperature at the length 100 millimeter, that is x is equal to L. We know the equation, theta upon theta p cos hyperbolic m in bracket L minus x divided by cos hyperbolic m. So I'm putting just in this equation x is equal to L. So this x is equal to L. So L minus L, cos hyperbolic L minus L 0, cos hyperbolic m into 0 0. So cos hyperbolic m 0 is equal to 1, and the equation will become 1 upon cos hyperbolic ml. I'm just putting the values 1 upon cos into m into L, and then I got theta upon theta b at x is equal to L is equal to 0.75. But we are interested not in theta, we are interested in finding out what is the temperature at the equation. So what is theta? Temperature at x is equal to L minus temperature of the fluid, that is T minus T infinity. And what is theta b? It is temperature at the base minus temperature of the fluid. So already we know theta b. We already calculated it is 180. We can write theta b into 0.75, that is this term, into is equal to theta. And what is theta? Theta is equal to T at x is equal to L minus T infinity. So I'm just bringing the T infinity on this side. So it will become plus. And T infinity plus this particular fraction 180 into 0.75 will be value of your TL. So if you calculate it, you will get temperature at x is equal to L is equal to 155 degree Celsius. This is our second answer. Now we are interested in finding out the temperature at x is equal to L by 2. So just put it whatever, once again same equation, x is equal to L by 2, that is 0.05. I'm just writing down x L minus 0.05 cos hyperbolic ml. So I'll get once again the value of theta upon theta b is equal to 0.807. Once again theta I know, and theta b, sorry, theta I can write in terms of temperature at x is equal to 0.05 minus temperature infinity, and theta b is already known. So if you use these values, so it will become 180 into 0.807 plus T infinity, and it is 165.37. I'll just go back to the last slide. I've got temperature at x is equal to L 155 degrees Celsius. Temperature of the base was 200 degrees Celsius. At 50 millimeter it was reduced to 155, and at sorry at 100 millimeter it was reduced to 155, and at 50 millimeter it was 165.37. So there is 50 to 100 length, the reduction is only of 10 degrees Celsius. And first 50, the reduction in the temperature is from 200 to 165, means almost 35 degrees Celsius. So this shows that the reduction is there, which is reducing, the pin temperature is reducing exponentially. Initially the temperature reduction is very fast, and slowly it will get reduced, and that's why at a certain length the fin will become redundant. Already seen that. So that's I'm telling you through a numerical. So this was our first issue, first problem. Let us talk about the second problem. A very long, now in itself very long means fin with infinite. The length is not specified. We are not alternative. We are not having any alternative. We have to assume that it is a fin with infinite length. It's simplest. Then very long 5 meter diameter. Once again, the diameter is very small. Has one end maintained at 100 degrees Celsius. The surface of the rod is exposed to ambient air at 25 degrees Celsius. Convection heat transfer coefficient is 100 watt per meter square Kelvin. What we have to find out? Determine the temperature distribution along the rod constructed from pure copper, 2024 aluminum alloy, and type AISI 316 stainless steel. So there are three materials: copper, aluminum alloy, of course 2024 alloy, and AISI 316 stainless steel. So these are the three different materials for which we have to find out the temperature distribution for a very long rod. Theta upon theta b is equal to e to the power minus mx. What is the corresponding heat loss from the rod? What is the rate of heat loss from the each of the rod? So let us do it. And second, estimate how long the rods must be for the assumption of infinite length. I already defined that if ml is equal to 2.65, that length corresponding to ml is equal to 2.65 is to be taken as the fin with infinite time. So we can use this assumption and we can find out what is going to be the infinite length for each of these three materials. So what is given? The properties are known. Thermal conductivity of copper is 398, aluminum is 180, and stainless steel it is very small, of course 14. So out of these three, stainless steel has got lowest thermal conductivity, aluminum is medium, and copper is the highest. So which material is suitable for which is the best material? It is copper, of course. So if you draw the fin, once again same type of picture because same type of rod, 5 millimeter diameter, 100 degrees Celsius. But in this case, we are not having the length. So let us assume that it is fin with fin with infinite length. So what are known things? Heat transfer coefficient, diameter, surface temperature, and fluid temperature. What is to find out? Temperature distribution, heat loss, how long it must be to add on the infinite length, and these are the assumptions. And then the assumptions are almost same: steady state, one-dimensional, constant properties, negligible relation with the surrounding, uniform heat transfer coefficient, and fin with infinite length. So with these assumptions, we can proceed and we can carry out. For infinitely long fin, the temperature distribution is already oh, discussed that it is equal to theta upon theta b is equal to e to the power minus mx. So if you expand the term theta, it will become t minus t infinity, and if you expand the term theta b, it will be tb minus t infinity. So I am just putting it in terms of temperatures, where m is hp upon kc raised to power 1 half, that is under root, and can be arranged because perimeter in this case is pi d, area of cross section is pi by 4d square. So if you put those values, you'll get modified equation 4h upon kd, okay, raised to power 1 by 2 pi are getting cancelled and 1 d is getting cancelled, and that's why, and that 4 will go up, so it will become 4h upon kd. Simple modification. So if you put values of h, d and k, of course h is same, d is same, only k is going to change for copper, aluminum and stainless steel. You'll get the values of m of for different materials are 14, 21 and 75.6. So note this, m is very small for copper, higher thermal conductivity, m is medium for aluminum, medium thermal conductivity, and m is very large for steel, lowest thermal conductivity. One. Now if you use this particular equation and if you calculate the temperatures at different locations, temperatures, and if you put it in the form of graphical calculations, of course it is suggested that you should at least calculate uh, 5 6 values for the temperature, maybe different values of x, say 10 millimeter, 20 millimeter, 30 millimeter, 40 millimeter, 50, 60, 70, whatever, up to whatever you can calculate, and if you calculate this, you'll get this. So of course I know that this is a lengthy problem, but you can solve it, and of course this is not the type of problem which is going to be there in the examination. This from understanding point of view, in examination you may ask to calculate the temperature for any one material, but here just I'm showing you so that you can compare. You see the temperature distributions are plotted here. The copper, the aluminum, and then the stainless steel. So these are going to be the this. Now what is observation from this? There is little additional heat transfer by extending the length of the rods beyond 50, 200 and 300 millimeter respectively for steel, aluminum and copper. Means steel 50 millimeter small, aluminum around 200 millimeter and copper around 300 millimeter. These are the lengths which are still useful. After that, the whatever length is there, that is becoming redundant. So this is what we can conclude from this particular graph. For a copper rod, we can calculate heat loss as once again the same equation under root k HPA into KSA into theta B. So you put the values in this equation, you get the heat loss from the copper rod as 8.3. We repeat the procedure for stainless steel and aluminum, you get 5.6 for aluminum and 1.6 for stainless steel. Note the heat transfer rate from copper is highest, medium for aluminum and lowest for the steel. Of course, we know that because of thermal conductivity of copper is highest, it's such as expected that it will carry large amount of heat in comparison with the other two materials whose thermal conductivities are less. So we can say out of these three materials, which one is the best material, best suited material for the fin? It is of course copper. A rod may be assumed to be infinitely long if you know that it is the condition is ml is equal to 2.65, that is L is greater than 2.65 divided by m. So if we calculate it for copper, you get this length is equal to 0.19 meter. So if a copper rod is to be used, it will become infinite, or it can be called as infinite if it is having a length of 0.15 meter, 119 meter or more than this. From the repeated calculations for aluminum and stainless steel, you get for aluminum it is 0.13 and for copper stainless steel very small 0.04 meter, and this was also visible from this graph also. And the infinite length for the steel is lowest, it is highest for the copper, and because of its higher length you can say that it is carrying more amount of energy from the surface. So fin point of view, copper is the best material in this three, among these three. We'll go for the third. Aluminum alloy fin 3.5 millimeter thick at the base and 25 millimeter long protrudes projects from a wall whose temperature is 420 degrees Celsius. The adjoining fluid is at 30 degrees Celsius and provides a convection coefficient of 11 watt per meter square Kelvin. Find the efficiency, effectiveness, and heat loss per unit width. This is important here. Unit width. Thickness of the pin is given, and the thickness is 3.5 meter at the base, and the length is also known. 25 millimeter is not low, so long. So thermal conductivity of aluminum is 200 watt per meter Kelvin. So with this information, as length is not too big, it is 25 millimeter only. We can assume that this is a fin with insulated tip, and we can solve this problem. So we have to use the equations for efficiency, effectiveness, and heat loss. What is given? Aluminum fin L is 25 millimeter, H is equal to 11, T is 3.5 millimeter, W unit width. So let us take it as 1 meter. That's very high, but as per the problem, we need to go. You cannot have the fin with width of 1 meter. If you're putting it on a wall, then only it is possible. But let us calculate for unit width. So let us take it, because we are using the units of meter for thickness. So let us use the same unit for width and let us take it 1 meter. K is 200 watt per meter Kelvin. TS is 420 given, and T infinity is 30 degrees Celsius. So with this data, what is calculated? What is to be calculated? Rate of heat transfer, efficiency, and the effectiveness. So what are our assumptions? Steady state, no internal regeneration, one-dimensional conduction, constant known properties, negligible radiation, uniform heat transfer coefficient, and of course, fin with insulated tips because the length is very small. Given. So straight, as I'm showing you the side view and the front view. Front view width is 1 meter, thickness. Sorry, this is width and this is the thickness here. This should be here. So this is the thickness, and uh, whatever temperature and other things are known to us. So we can calculate perimeter, so rectangular cross section. So W into T, sorry, 2 into W, that is 2 meter, because you may ask me, sir, why W, sorry, thickness is ignored, because in comparison with this, what you call thickness, width, the thickness is very, very small, and that's why it is ignored. If you want, you can consider, but that is not going to make any difference in the answers. Cross section area, of course, here we cannot ignore the thickness, and that's why it is considered, and it is found to be 0.0035 meters square. Theta b is Ts minus T infinity, 420 minus 30 is equal to 390, and ml we can find out by putting the values of all these parameters in the equation, and it is 0.14. So for this, with this data, P is 2 meter, area of cross section 50035 meter square, and ml is 0.14. We can use the equations, heat transfer rate for fin with insulated tip under root hp into ks into theta b tan hypergamy. Putting the values, all the values are substituted, and finally the things are calculated, and it was found to be 213 watt. And fin efficiency of the fin is equal to q fin upon q fin max, and that is we know already, tan hyperbolic ml upon ml for a fin with insulated tip. And if you put the values of ml in this equation, you can calculate the efficiency 99.35. It's very high efficiency fin. It's a very good thing. And then effectiveness of the fin, same calculations, under root kp upon hs into tan hyperbolic ml, putting the values, and finally effectiveness is 14.17. You can just go and recall that 14.17 is a good value, because if it is more than 1, then we are saying that the fins are effective, and is 14 times more than that. It means that if the fin is not there, if the heat transfer rate is 1 watt, and if the fin is provided, the heat transfer is going to be 14.17 watt. It means that much increase in the rate of heat transfer. So you can, other words, I can say that if I know the Q fin, that is 213 watt, and if I know the effectiveness, and effectiveness is what, Q fin upon Q, sorry, Q fin divided by Q no fin. So I can calculate the Q no fin by knowing this 217, sorry, 213 divided by 14.17. So I'll get that much is the rate of heat transfer when the fins were not there. Fins was not there. When the fin was not there, that much was the rate of heat transfer. And there is 14.17 times increase if the fin is provided. So it's a good thing. So fins use can be justified in that way. So in this particular lecture, we have discussed about the numericals on the adiabatic fins, numerical on a infinite fin, and a calculation of the fin performance. We have solved three numericals for three different conditions, and that's the end of the second unit of our syllabus, which in which we have considered two types of problems. One is heat generation, and the second one is fins or extended surfaces. In the next unit, we'll be talking about unsteady conditions. So in the next lecture, I'll be talking about the unsteady conduction problem. Thank you. Thank you very much.